and talking about microstructure, this is what we're going to be talking about today. You see the different colors? This is the different orientation of the grain after it was deformed. We have high angle grain boundaries. And believe it or not, like this guy's over here, you know what this is? Those dots here. What do you think those dots are? Huh? Look at the scale. This is 5 nanometers. 5 nanometers is how many angstroms? 5 nanometers, how many angstroms? I told you in another class. You should remember. How many angstroms in 1 nanometer? 10. Okay. So these are atoms that now we can see. Now, if you want to do fast Fourier transform and inverse fast Fourier transform, you see this? This is the distance between atomic planes. So 0.2 nanometers should be space here. Is how many angstroms? 0.2 nanometers is how many angstroms? 2.1 angstroms. Okay. All right. Now we're going to talk about atomic structure. And specifically, we're going to talk about crystalline versus amorphous. And last time we discussed electronic structure, and now this is all in the past. This was quantum mechanics and the structure of the atom and all that good stuff. And now what we're going to assume is that the atoms are hard spheres like this. Okay? We're going to start with metals. We're going to talk about how crystal structures are characterized. And we'll do some crystallography a little bit. We'll talk about directions and points and planes and kind of like geometry stuff. And then we'll do this famous example of calculating density. What is density, by the way? Who was the first guy who figured this out? By taking a bath? How do you measure density of something? No? Yes? Eureka, who said that? What was the guy's name? Archimedes. So, have you been to ancient Rome? Anybody? Okay. Have you been to Greece? I haven't been to Greece, but my question is, how did those guys figure out that all matter consists of atoms? I mean, now we can see it, but back in the day, like, how did they figure it out? Stuff. I like that stuff. All right. So, have anybody seen a truck full of bricks? Okay? You know what I'm talking about? A pallet of bricks gets delivered here. Imagine. And it's coming down here. The truck pulls beep, 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 beep. And the forklift brings a pallet of bricks. Wrapped around nicely in plastic wrap. Okay? Imagine that. And now we're going at it. We cut the plastic wrap and we just push those bricks over here. We push it down. and the bricks are laying down. Big, huge pile of bricks. Imagine? Okay. Which pile is going to occupy more volume? The one that's neatly packed, brick to brick, or the one that's piled up randomly? Piled up randomly is going to occupy space. I know what you mean. We all know what we meant by saying it occupies more space, right? But I want to talk about volume, because in the end, this is the right term to use. Does that make any sense? Okay. Remember the well concept that we talked about last time? This is the energy, and when everything is neatly arranged in a closed, packed fashion, and by the way, this is the closed, packed plane. Plane means that I take these balls and I put them on a plane, and there's no better way to pack those balls. You cannot pack them more densely than this. There's no other way in the plane. See that? Does that make any sense? So like if you take your 3 fingers like this, or 4 fingers, there's no more efficient way for you to pack those spheres in a plane. Right? Now we're going to talk about 3D a little bit later. But whenever they are randomly positioned, then what actually happens is, on average, the neighboring distance is a little bit larger, and they're occupying more volume, but also you can see that in this position, the energy is lower, right? And the system, all of the systems tend to go towards the minimum energy state. Does that make any sense? Okay. Same exact material. It's called SiO2 tetrahedra. Tetrahedra is red ones are silicon and blue ones are oxygen. And here's a periodic array in 3 dimensions, and it is crystalline, because you can see that it's kind of like that pile of bricks that's neatly arranged. And if you ever go to Costco, you can buy yourself a chandelier that's $1,000. And the reason it's $1,000 is because the little pieces are made from quartz. And quartz is a single crystal. And quartz has this interesting optical properties. When you shine white light at this crystal, it gives you the full spectrum. It gives you the rainbow. Do you know what I'm talking about? Okay. Now, how about that glass over there? See, there's a special room over there with audio, visual, and who knows what else. How is that glass different from quartz? Chemically, it's the same. The chemical formula, it's actually the same as the sand in Clearwater Beach. It's SiO2 is the chemical formula. But the structure of it is different, because for the glass, it's random. And through processing, we achieve that. How? We take a melt, and there's melt. And we can take sand, and we can melt it. And then, when it's being poured, and we're going to talk about processing of ceramics when we do, that's how that glass is made. Now, if you were making a plasma TV, who has a plasma TV? Not even me. Well, you do still, plasma? It must be a good one, right? Why do you have a plasma TV? Quality?
Quality.
Okay. How big is it?
55 inches.
55 inches. So,
Dang.
but its top end was like $10,000 back in the day. You don't know? But it looks good, right? Very bright. So at some point, this glass technology became very important. Why? Because everybody wants a big TV. Okay? But the difference is that amorphous, the synonym of amorphous meaning, and please listen, no long range order. There is a short range order. Why? Because the backbone is the same, this. But the way the structure is put together is like that pile of bricks. And that is going to determine very important properties like glass transition temperature. And we're going to apply this concept to polymers, not just ceramics. So, nanocrystalline materials have no periodic arrangement. And it occurs for two reasons. One is the structure is complex. The molecule is very big. The head doesn't know where the tail is. And that's where we're going to talk about polymers. Or it happens very fast, so that there's not enough time for this thing to crystallize. And who controls that? A process engineer to control the process. I just showed you how the structure can be controlled. And obviously, as a result, the properties are going to be very different. Okay, metallic structures and the atomic packing of metals. Metals are very dense. Why are they dense? Because the bonds between those elements, between those atoms, are non-directional. What does that mean, non-directional? I mean, obviously it happens in 3D, but we're going to use this class as a plane, right? The bond is formed between the nearest neighbors, okay? So two atoms right next to each other form a bond. They're like secondary effects. I mean, 2 seats away, there's still maybe some, but not as much as two atoms are next to each other or are touching each other. So as a result, this nearest neighbor distance tends to be small, which results in lower bond energy. And there's also high degree of shielding, meaning that we have this free electron cloud. You remember in chemistry about shielding? Remember the concept? Only the valence electrons are participating in the bond. The rest are shielded from the structure. And also, the crystal structure, which we're going to talk about today, is simpler compared to ceramics or polymers. So, let's dive into those structures. And one is called simple cubic structure. There's an atom at a corner of a cube, like this. Okay? And we can section it. So this is your simple cubic structure, like this. If we are to draw this in 3D, by the way, this is called unit cell. And if we draw 8 unit cells, we can see that this atom here, which is highlighted in red, has how many nearest neighbors? Well, we can just simply count. There are 4 in the plane, there's 1 above and 1 below. So there are 6 nearest neighbors. And by definition, coordination number, not for this structure, but for any structure, is the number of the nearest neighbors of an atom. Does everybody understand the word nearest? What's the physical meaning? The closest one, the minimum distance. Okay? There are other atoms, but the distance is larger. So like this one over here compared to this two, there are atoms, and it's all positioned in 3 dimensions. Okay? Now, the other thing that we're going to do, and we're doing, is we're taking an atom, which we treat as a sphere, and we slice it. Okay? So the concept is this, is that this atom is going to belong to more than one unit cell. And for the crystal, the unit cell is the repeat unit. So corners of those atoms are located at 8 corners of a cube. And there's something that's called closed pack direction. And direction is when the atoms are physically touching. And you can see that, like in this direction or in this direction, atoms are touching, but they're not touching in this way. They're not touching here. You see that? So, close packed. You guys have a close pack arrangement in this row. There's no more space. Okay, so you are close packed. And this is in terms of the row. And the same thing applies for the second row, and the same thing applies for the 3D on top. Any questions about this? So far we learned about the coordination number, which is the number of the nearest neighbors, and we learned the term close packed direction. Now I'm going to give you the definition. So the coordination number is the number of the nearest neighbor of touching atoms. And what we're going to do is we're going to calculate what is called atomic packing factor. And that is equal to the volume of the atoms in the unit cell. And we assume that those atoms are hard spheres divided by the volume of the unit cell itself. And what does this physically mean? Well, if we go back up here, this is the unit cell. What is the volume of the unit cell? Well, this is a cube, so we have this and this and that. So this times that is the volume of this unit cell, right? But what is the volume of the atoms in this unit cell? You see, because we have spheres here, and this is 1/8 of a sphere. You see that? So if you think about it this way, if you take all these pieces, which is 1/8, and put it all together, then how many whole atoms are we going to have? Just one. Do you get the concept? It's not that hard. So let's figure this out on the simpler one before we move to a little bit more complicated ones. That's the idea. And there is free space. You can move in there and it's rent-free. If you can fit in there. So what we're going to do is we're going to calculate how much free space is there. I mean, to us, it looks dense, but it's not on the atomic scale. Does that make any sense? Do you get the concept? Okay. So let us calculate the atomic packing factor for a simple cubic structure. And we assume that the radius of the atom is large r. A is the lattice parameter or unit cell parameter. So if this is A and this is R, and because this is the radius and they're touching each other here, then we can say that R is equal to half of A. Now, how many fractions of an atom do we have here? We have 4 on the top and 4 on the bottom, so overall how many? 8. And what fraction of a sphere is this? Like, if you were to put them all together, what are you going to have? You're going to have one sphere. So we have 8 fractions of 1/8 of the full atom, and there are 8 of them. How many full atoms do you actually see here? 1. 1 full atom. You can take those pieces of the puzzle, you can put them all together. This is forming the top half of the sphere, this is forming the bottom half of the sphere. Altogether, just 1. 1 full atom. So in a unit cell, for simple cubic structure, we have 1 atom per unit cell. What is the volume of a sphere? 4/3 pi r cubed. Okay? So the volume of 1 atom that has a radius r is 4/3 pi r cubed. And what is the volume of a cube with a side A? A cube. Volume of a cube with a side A. A cubed. Okay. I was going to break it down and ask you what's the area of a square. A squared. And for the cube, it's A cube. It's A squared times A, which is A cubed. Does everybody get that? And the volume of a cube. Okay, you got it? Good. So now, what we do is we divide the volume of 1 atom times the number of whole atoms in the structure by the volume of the unit cell. And what do we get? A cancels out. We get 0.52. 0.52 in percent is how much? 52%. And what's the rest? 48%. There's 48% of space in this structure. Almost half is empty. You guys are paying rent. We should move in. You know what I mean? Okay. This is a simple structure. Do you have any questions? Does that make any sense to you? Yes? Okay. All right. Let's look at something a little bit more complicated. Body-centered, by the way, the notation for simple cubic is SC. So that's what it means. SC is simple cubic. The next one is body-centered cubic structure. Why is it called body? Because it's my body. This is the body. And there's another atom right there in the middle. Okay? So there's a full atom that is stuck there inside that cube. And you see what it does? It kind of like spreads these guys. They're no longer touching. How are these atoms touching? They're touching along the diagonal of a cube. And this is a little better way to pack the atoms together. So we have 8 cube corners with a single atom at the cube center. How many whole atoms are there per unit cell now? 2. Which are they? We have 1/8 times 8 plus another one. Somebody just moved in. Another one in the middle. So for the body center cubic, and the reason it is called body center cubic is because this is a body and centered in a cube. So that's the way to remember BCC structure, body center cubic. Now all of a sudden we're packing 2 atoms per unit cell. Okay? The coordination number is still 8. Why? Because this guy has 8 neighbors, 4 on the top and 4 on the bottom. Same coordination number, but now there's a better way to pack those hard spheres that have the same exact diameter or radius. By the way, the book comes and used to come with VMSE, whatever that thing stands for. Visual Material Science and Engineering. And believe it or not, when I started to teach this class, it came on a floppy. So please Google Callister VMSE. Because it's another visual aid for you. Okay? And here's the BCC. You can rotate it in 3D and why can this be useful for you? Well, if you ever need to do a visualization, you can just take a screenshot. Let's see what else we have here. There's no simple cubic, so we'll just stick to the lectures for that. Okay, let's calculate atomic packing factor for BCC. And this is a little bit more complicated. If this is A, and this is R, then what is the direction where atoms are physically touching each other? They're touching along this line, which is a diagonal of a cube. Okay? So if the height here is, this is A. This is always A. A is the parameter of the unit cell. Okay? If one side is A, what is the diagonal of the base? This. It's going to be the square root of A. And what would be the length of the diagonal of a cube? It's going to be the square root of 3 times A. Does everybody get that? So we have a right triangle. And what I'm showing you here are these 3 atoms. This one, and that one that are touching along the diagonal of the cube. You see that? Does everybody see that? Okay. So now, how many radii there are? There's 1, there's 2, there's 3, and there's 4. Does everybody see that? So we can say that 4r is equal to the square root of 3a. If this side is a, if this is square root of 3a, square root of 2a, then using the famous theory of Pythagoras, this hypotenuse is going to be square root of 3a, right? That's where it comes from. And the same thing is this diagonal here is square root of 2a, because this is just here in the plane. So we have the right triangle. This diagonal here is square root of 2a. The diagonal of 3D is square root of 3a. Why? Because a squared plus 2a squared is equal to this. So 1 plus 2 is 3. That's how we get square root of 3 once we take a square root of that. Does everybody understand this part? Why this is square root of 3a? Okay. Does everybody see that this is 4r? 1, 2, 3, and 4. So we have this simple equation that 4r is equal to the square root of 3a. And then r is equal to the square root of 3a over 4. That is the radius of an atom. How many atoms do we have for a body-centered cubic structure per unit cell? Full atoms. We just discussed that in the previous slide. 2. We have 1/8 at each corner and 1 in the middle. So we have 2 atoms per unit cell times the volume of 1 atom. 4/3 pi r cubed. So instead of the r, we plug this into here. So this goes here, and this becomes 2 times 4/3 pi square root of 3a over 4 to the 3rd power. And the volume of the unit cell is still a to the 3rd. And once we just do the simple math, cancel out the a to the 3rd, what do we have? 8/3 pi times the square root of 3 over 4 to the 3rd power, and that is equal to the 0.68, or 68%. So for body-centered cubic, the atomic packing factor is 68%. We just improved the efficiency of packing from 52% for simple cubic to 68. Any questions about this? Before we go to the best scenario. And the best scenario is called FCC, or face-centered cubic. So there's half an atom on each face, like this.
No, tenemos uno.
Okay.
Did they
And that's what it looks like in 3D. By the way, there were some examples. Most of the metals, like aluminum, copper, gold, platinum, nickel, they have this kind of structure. And if we were to calculate the coordination number, the number of the nearest neighbors, for the FCC structure, it is 12. So from 8 we go to 12. Okay. Now, calculating the number of full atoms for this structure is a little tricky. Why? Because we have 6 faces, right? But we only have half an atom. So we have 6 faces times 1/2, which is 3. And then we have 8 corners, and that's 1/8. So we have 3 plus 1 is how much? 4. So from 1 for simple cubic to 2 for body-centered cubic to face-centered cubic, now we're packing 4 atoms per unit cell. Let's calculate the atomic packing factor for this. Where are the atoms touching here? Well, they're touching along the diagonal of the face. So like this. If the unit cell is A, then this diagonal is going to be square root of A. And how many radii do we have here? 1, 2, 3, and 4. So we write that 4r is equal to the square root of 2a. And that means that the radius is equal to the square root of 2a over 4. And we take this and we plug it into the volume of an atom, which is 4/3 pi, whatever this r, cubed. And how many atoms do we have per unit cell? We calculated in the previous slide. 4. So we multiply it by 4, and we divide it by the volume of the unit cell, which is 8 to the third, and we get 74%. And it doesn't get any better than that. There is no other way to pack those spheres in a more denser way than in this kind of arrangement, which is face-center cubic arrangement. Now here comes the handout. And I'm going to explain to you what this physically means. Okay. This is a closed packed plane. And then the next plane comes into this little indent like this. So you can see that, like, for simple cubic structure, we have an atom on top of an atom. So it's A, the same arrangement. So for this, it's A, and this is a B arrangement. Okay? And then, the third plane, there are two ways to put it together. One is in the same. So this is A, this is B, this is A again. Okay? And then, the third way is to put the third layer into a different position. That's neither A or B. So we're going to call it C. This, you can see it here. So although the packing density is the same, because it's the same dense plane, AB versus ABC versus ABC, and I want to give them to you together so you can compare. But for this one, you have to rotate it to actually see that it's ABC. And I'm going to give you another half a plane or full plane, and you can play with it and see which way, because there are two ways you can position it. All right? Just whenever it's going to make it to the end. This was somebody's homework 20 plus years ago. But pretty neat. It's not that hard, right? So we're operating with the hard spheres. I mean, I do have the ping pong version, but I figured, and it gets broken over time because this is hot glue. It's amazing how long this still serves its purpose. Okay, so we have A sides, B sides, and the C sides. You guys cannot believe the technological difference between this AB versus ABC arrangement. You just can't. And I'm going to explain it to you when it comes down to that. The elements that pack in, oh, by the way, it's called hexagonal closed packed. I didn't get to that yet, but okay. So you can see for the stacking of ABC, it's the diagonal of a face, ABC. And I gave you the H so you can actually see it. But for ABA, it's called hexagonal closed packed, HCP. It still has the coordination number of 12. The atomic packing factor is 74%. The ideal ratio between A And C, see this is A, unit cell parameter. We have to introduce another one, which we're going to call C, because there's no other way to describe the structure. I'm passing this around so you can, see it. Examples. Oh, by the way, there are now 6 atoms per unit cell, if you do the calculation. And for ideal ratio between C and A is 1.633. Titanium. Titanium has HCP structure. And that's why titanium is a very good material, very good structural material. If you have an iPhone, allegedly the case is made out of titanium. I don't know how that helps. You drop this thing, it's still broken. It must be a marketing gimmick. But titanium is very hard to process. And the reason it is very hard to process is because it has HCP structure, so the number of slip planes and slip systems is limited. Do you guys get this so far? Not so hard? Okay, now let's do this problem of calculating the theoretical density of a metal. The density is mass of all the atoms in the unit cell divided by the total volume of the unit cell. How can we break it down? We have the number of atoms per unit cell times the atomic weight, right? And the atomic weight we get from the periodic table, divided by the Avogadro's number, which is the number of atoms per mole, divided by the volume of the unit cell. So the formula for the density, ρ, is going to be equal to the n, the number of atoms per unit cell, times the atomic weight, divided by the volume of the unit cell, which is going to be a cubed for a cubic. Most of the metals are cubic. And divided by the Avogadro's number, which is 6.022 times 10 to the 23 atoms per mole. And if we look, for example, at chromium, and chromium has BCC structure, and I'm going to tell you how we know that it has BCC structure. The atomic mass is 52 grams per mole. The radius is 0.125 nanometers. For BCC, how many atoms do we have per unit cell? 2. And A is equal to the 4R divided by the square root of 3, or 0.2887 nanometers, and the volume of the unit cell is A cubed. So we take that A and we cube it. So we have 2 atoms per unit cell times 52 grams per mole divided by 2.406 10 to the negative 3, which is the volume of the unit cell that we just calculated, divided by the Avogadro's number. And we get 7.19 grams per cubic centimeter. The real true density of chromium is 7.15. How close is that? It's pretty close. It doesn't really prove anything, but at least we can see that the close packing, the models that we just use of hard spheres, it works. Any questions or comments? All right. This is the chart that plots the density of metals ceramics, polymers, and composites. And by the way, does everybody understand what a logarithmic scale is? This is a logarithmic scale. Okay? What's plotted here is the power of 10. And we go to 1. And we go to 2. You see, because this is a power of 10, the distance until we get to 10 is nonlinear. And then it goes to 20, 30, and so on and so forth. In case you didn't know. And it's okay. This is a logarithmic plot. Meaning that the scale on the y-axis is logarithmic. Meaning that we're plotting the power of 10. And it's very nonlinear. And the reason I tell you this is because sometimes you're going to have the data that's presented to you in this way, and a common problem for a student would be to try to figure out what is the density of aluminum. Or what is the density of magnesium? You have to realize that this is a nonlinear scale. This is a logarithmic scale. So this is 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.91. You see that the distance here shrinks as we get to the next power of 10? And some of you think, oh, I know this, but some of you think, oh, this is the first time I see it. And that's the reason why I emphasize it, so that we're all on the same page in terms of what the logarithmic plot actually means. Is this familiar to you? You know what a logarithmic scale is? Good. Where did they tell you about this first time? Yeah. Yeah? Oh, decibels. Why did you have to deal with decibels? For physics, you have to deal with decibels. Anybody else was dealing with decibels? Where, in physics? Anybody else? Does anybody know what decibel is? What is a decibel? What? Measurement of sound? Sound volume, right? Okay. And why is it logarithmic? Because I can be whispering like this and you're not going to hear shit. Oh, I have a microphone, you can still hear. Anyway, the reason is they use decibels. That's where the power of 10 is introduced, is because the difference between 1 and 2 decibels is what? In terms of the noise level. All right, how about 10 and 20? It's the logarithmic scale, it's the power of 10. By the way, when do you hear about decibels? If you have a high-end speaker system, they measure the sound in dB, right? City noise ordinance is also in dB, in case you didn't know. So if you have a party, and depending on where you live, you cannot have the noise level above a certain amount of decibels. And those guys, they have a decibel meter. In case you haven't seen it, it's a device that measures the level of the noise. Have you ever seen anything like this? You've never seen a decibel meter? Where did you see the decibel meter? Yeah. Okay. That's not a good place to see it. If you ever seen any of the Hollywood shows, you know, those people start to cheer, and they have a decibel meter to measure if they like singer A, singer B. Have you ever seen anything like that? No? Okay, well, pull up some stuff. You know, it's going to be more than 10 seconds on TikTok, but maybe it will be entertaining. Going to this, we see that the most dense materials are actually metals. Why is that? Because metals are closely packed. And they're closely packed because they have metallic bonding. They're also heavy. And, you can look at the atomic mass. Please remember that the atomic mass is given per mole. Also, ceramics have lighter elements like oxygen or carbon. And polymers are lower density because very often they are amorphous, and also they have lighter elements like carbon, hydrogen, and oxygen. And composites are a mixture. So, do you think it's cool or not so? We've taken some really advanced chemistry and physics that we covered in the last lecture and said, okay, let's use spheres, and spheres represent atoms. And we just calculated that the best packing is 74%, meaning that there's 26% free space. And if you look in terms of your understanding of this materials business, is you got a ping pong ball, you got a tennis ball, and you got a basketball. If you look at the distribution of atoms and their sizes, the relative sizes are about that. We start with hydrogen, which is a tiny little guy, and we go to much bigger atoms that are like basketball. So you can imagine that if you take basketballs and you put them together, the spacing, there is a channel right there. You can actually see through your 3 fingers. There's a channel. So this is a channel, meaning that a smaller atom can fit in that channel. And this is going to determine a lot of very important properties for the materials, like diffusion. And that is going to determine the properties of the materials. And you, as the process engineer, you're controlling the process. And as a result, you're controlling the structure. As a result, you're controlling the properties. A single crystal is the whole specimen is a single crystal. Quartz is a single crystal. Diamond, anybody has a diamond? Does anybody have a diamond? No? Diamonds are forever. Are they? Can you crush a diamond with a hammer? You can. Can you make graphite out of a diamond? You can. How? Just need to heat it up. And then your diamond is going to turn into pencil. So I always ask myself a question. Why does it cost so much? Have you asked yourself a question? Why diamonds are costing so much? They're hard to make. Who makes diamonds? I mean, there are artificial diamonds. And they do have very important technological applications. I understand why gold is expensive. Do you know why gold is expensive? What? It's limited. It is limited, it's true. There's a journal called Gold Bulletin. And Gold Bulletin will publish your paper for free, and will publish your pictures in color for free. Normally you have to pay like $1,000 a page if you want to publish in color, like in print. And I want you to tell me, what is the size of a gold cube if we take all the gold on planet Earth? Please look it up. What is the size of a golden cube of all the gold that's available on planet Earth? While you look, we go back to single crystals. This turbine blade is a single crystal. What is it? 23 meters. How much is 23 meters? About 15 meters or so, roughly. So 23 meters is, you see what I mean? That's how much gold we have. I mean, there's more in somewhere else, but we're just yet to take it. Okay. These are diamond single crystals. They're relatively small. They're very good abrasive materials. There's an example of a quartz single crystal. And here's a man-made. Doesn't say what material because it's proprietary. Most of the materials are polycrystalline. So what we mean by that is that each grain here is a single crystal, and each grain has a certain orientation. So here we can see, and this is 1 millimeter scale. So this is a large grain, this is a small grain. And the other thing I need to tell you is that material science and engineering is all about finding a length scale. We care about the size. We start with the size of an atom. We go to a feature of a microstructure, which in this case is the grain size. This is niobium hafnium tungsten plate with an electron beam weld. And each grain is a single crystal. And then sometimes those grains, like for this structure, they could be from 1 nanometer to centimeters. Or they can be really at the nanoscale. This brings us to anisotropy. Anisotropy means that the properties are different in different directions. And I'm going to explain to you. So, in this case, the properties depend on the crystallographic orientation, or in the crystallographic direction. This is a BCC iron. You can see that along the diagonal, the stiffness or the elastic modulus is 273 gigapascals. But along this direction, it's only 125. Why is that? Because for the diagonal, that is a closed, packed direction, meaning that the atoms are touching each other along this direction. I'm passing around those things that you're looking at, and you can see which direction is closed packed. If we're looking at this here, these two atoms are not touching each other. They're like this. So if I'm pushing this way, you see, I'm not touching on two atoms that are right next to each other. They're not nearest neighbors. So what this means that if I push this way, there's going to be a force projection that pushes this way, and then eventually pushes this way. This is why the stiffness is more than half along the edge of 125 gigapascals versus 273 gigapascals. And this is called anisotropy. And the reason we as engineers don't really care about it is because most of the materials are polycrystalline, and those grains are more or less randomly oriented so that it averages out. But if you're dealing with a single crystal, you have to worry about this. You have to worry about anisotropy. Now, anisotropy can be any kind of property, not just the elastic property. Anisotropy versus isotropy. 20 micron scale over there. Each one is an individual grain. Please remember, each grain is a single crystal, meaning that it goes, all the atoms are positioned in the same way. The orientation of this grain can be different in 3D, and that's what I showed you in that paper. Okay? Now, sometimes the materials can have what is called texture. And for example, if we take this microstructure and we roll it, or we extrude it, then the grains get elongated along the rolling or extrusion direction, and that gives the structure texture. And then again, this material would become anisotropic because of the deformation texture. You think this class is cool? No? Yes? I'm doing my best. I want you to get excited. The reason I'm standing in front of you is because when I was in school, a teenager, I told you the story, right? They brought me to university and there was a TA or a graduate student that came out with a liquid ball of nitrogen. And they took a tennis ball and they put it in and it dropped and caught my attention. What cars are you guys driving? Let me ask you a question. If you were to choose between Honda and Hyundai, which one would you choose?
Honda.
Why? How do you know that? Experience. Okay. I got a Honda, but about the reliability part, you need to get a lot of data. The reason I picked up Honda is because the engine block is made out of aluminum, and for Hyundai, it's made out of cast iron. So it's you really have to be a material scientist to get that joke. But it's true. So I bought a Honda. It needs to be fixed a little bit, but my daughter wrecked it a couple of times only. So I picked up the Honda because the engine block is made out of aluminum for Honda Fit versus a cast iron for Hyundai. Do you have any questions or comments? Did everybody hear a pitch about Wiley Plus? Please make sure you get the Wiley Plus and forget about fold. I'm sorry, it's not my fault, but I'm sorry. Maybe it costs you a little more. Okay, please come to the help session tomorrow, and I'll see you Tuesday.